Welcome to you all to this symposium in honor of Bart Haar Romeny. My name is Josien Pluim and I'm your host for today. I assume that most of you know Bart very well, and then you must know that scientifically he has two great loves. And one of them is Mathematica. It formed the base for many of his achievements, if not all of his achievements, and it resulted in him earning the Wolfram Innovator Award in 2013. Bart's second scientific passion is teaching. Nothing pleases him more than to enlighten students on image analysis and to pass on his enthusiasm for science. He therefore jumped at the chance of organizing this symposium that is meant to give you an overview of some exciting science, both some recent results and pearls from the past. The fact that so many of you are here present today to enjoy what he has put together for you, I'm sure will delight him. It is a rather packed program today, as you may have seen, so perhaps I should warn you that Bart used to plan his group scientific meetings during lunch breaks. So I hope you brought a sandwich. And one last question, could you please all check your mobile phones to make sure they're as silent as can be? And with that, I'd like to move on to the science of today and to our first speaker. First speaker is Professor Paul van Waas. He's Emeritus Professor of Radiology at the University Medical Center Utrecht. He and Bart go back a long way, at least as far back as 1983, when Bart started as a physicist at the UMC Utrecht, or the Academisch Ziekenhuis Utrecht at the time. And he will reveal some facts about Bart's early years in science.
Good morning. Dear Bart and Hetty and friends and colleagues of Bart, it's a real great pleasure that you have invited me to give this lecture. In the beginning it was quite cumbersome since I had to go back to the early years of 1983. Since Bart, you arrived with us when we were still working in the old 110-year-old hospital at the Catharijne Singel in the medieval center of Utrecht. And you left Utrecht when we were working at the campus of the Eindhoven in Utrecht. And it is an amazing period. I didn't realize you. As a young scientist, you did a beautiful PhD thesis on your own musculature, making microelectrodes and introducing in your own calf. And that was highly scientific. And you draw the attention of Peter Lever, who advised us to appoint Bart. And so you came, and then after 2002 you left, but having a great time with my wife in Chicago. So in short, to end this lecture, you have been a disruptive medical physicist. Everything changed. And you became a major player in the European radiology, leader of the Dutch Picture and Archive and Communicating System project, and an active member of the European Congress organization. So now I'd like to share you a bit of history. The board of directors advised us to hire a medical physicist to protect us from the great dangers of radiations, and also to take care of the maintenance and purchase of equipment. Until then, our own prerogative, we didn't need a medical physicist. And Peter Lever, who is present here, he suggested that Bart was not dangerous, but a highly interesting person, but we didn't like to see him as a radiation buster. But nevertheless, we have followed the advice of Peter Lever. And so you see Bart working at his first desk, Nobody would tell he became a great gardener when you see the deplorable state of this plant. There is an analog telephone, there is a light box, and there is no trace of computer of informatics at all. But nevertheless, he was functioning well. We, on the contrary, were working in a damp central reading room, packed with auto alternator, with a lot of heat, and sheet film only. And there was no trace of computers, of image processing yet. A terrible place. And then something strange happened. Jan Koenderink invited Steve Peiser to work with him, and he proved to be a deus ex machina, since he started to work with Bart and Karel Zuiderveld, also present here today, his first co-worker. And Steve brought with him the beautiful software developed in his own department. Oh, sorry. And one of his co-workers, Mark Levoy, developed 3D rendering, a novum at that time. And this is the work of Karel Zuiderveld with closed vessel projection instead of maximum intensity projection, a real wonder. And then Bart made a major step that changed everything. Karel Zuiderveld looks harmless, but he was planted in the middle of our damp reading room, so he could check immediately if it was effective what he was doing. And we as radiologists could witness the wonders of medical imaging. And he did a good job, so he was promoted to Max Viergever's department of the Image Science Institute and got a beautiful, great office, far better than he had with us. And here's Karel still working. And he became a senior developer with Vital Images. And Bart was just following his visionary passion for understanding the visual system. Bart told us a dream of total conversion from analog to digital. This is our main reception desk with an alternating archive for paper folders with patient data, and everything was analog, a huge archive with sheet film, and this is a holy hour, a film discussion session with a so-called hot seat, and it's just sheet film and auto alternator. An important man was also André Achterberg. He was simply gluing reports on paper folders, but he was the man who designed the logistics of a future PAC system. All the algorithms needed. A very important step forward. Bart arrived in 1983, and already in 1984 he explained to us that the construction plans for our new hospital, where we should move in 1989, was not coping with the near future of digitization. So we had to drill huge air vents in thick concrete like this. We had to make extra space for huge computers. And when we moved in 1989, the computers were very small, produced no heat anymore. And we could place an extra CT scanner in the computer room. And we didn't PACS at all, but it was a visionary approach. You have to realize that we were already going digital in '76 with dual slice body CT, digital ultrasound, digital subtraction angiography, and magnetic resonance and spiral CT. But everything was analyzed on a standalone viewing console, and then the sheet film produced, mounted on viewing boxes. A very cumbersome method. But in the meantime, Professor Karl-Heinz Hörne in Germany developed the Visible Human Project, a cadaver sliced in very thin slices and then reconstructed again. And that was the landmark how we could work with CT slices and MR slices. And the industry developed together with the American College of Radiology a so-called DICOM standard, so you could couple the different species of equipment. The 3D images were highly preferred by clinicians, as the beautiful work by Frans Zonneveld, with a lipoma and a terrible tumor, and successfully operated upon. But the radiologists, they said, no, that is for simple clinicians. We don't need 3D images. But Bart kept up high spirits and celebrated every landmark in the meantime. But the greatest thing was that Bart returned from Washington University in St. Louis and got a grant to build the first concept digital reading room in Europe. And there is a huge room for computers, and he could set up the ideal concept of a reading room with beautiful ergonomics. So the cathode ray tubes, the bulky ones, were mounted in a tilted way in the desk. And we had to digitize everything, since the whole department was based on sheet film. But instead of 3 days, we could report everything within 24 hours. But this is nowadays ridiculous. This is sheet film digitized again, and then digital on a screen, but still analog. You could only look at the images and not work with the images. And this is the standalone unit for the internal medicine department. But nevertheless, everybody was happy. So in 1989, the PAX project ended. We moved into the new hospital. The system designed by Bart was 4 times more expensive than our film-based system. The DICOM coupling even Philips equipment to Philips equipment was impossible. And the computer data network had a limited capacity. And it took 2004 to realize all the dreams by Bart. So 20 years after his visionary initiative. So he had a beautiful congress in Eindhoven in 1988. But in the magic year of 2000, we were still looking at sheet film and looking at monitors, but not a PACS. But this sounds negative, but you have to realize Bart was among the 4 greatest pioneers of Europe. The man who started all this was Oscar Craig, but his technology failed, but he had the first initiative. Then Bart had the vision to couple a hospital information system and radiology information system to PACS and view the typewritten reports on the workstation in the digital reading room and the workstation in the clinic. Then Michel Hosteau, from Brussels, he made a high-speed network, and Walter Ruby from Austria had the guts to create a totally filmless academic hospital, fully digital. And it worked. Amazing. So, speaking about Vienna, Bart and I, we went to the European Congress, and Bart was quietly astonished that there was no image processing visible yet. So in 1997, he took the initiative to invite 10 top academic research groups to show their image processing results within radiology. And it had a beautiful name, that alley of exhibits, the Golden Mile, later on Matrix and Imagine. And since 2014, it's now completely integrated among the main topics of the European Congress, so radiomics, deep learning, and computer-assisted diagnosis, things we will discuss today. And the same is happening in Chicago at the Radiological Society. So, in short, when Bart arrived, it was hot and damp and sheet film, and we had no idea what was waiting for us in the near future. And now, today, in 2017, all the dreams of Bart are realized. Everybody is reporting on at least 4 screens, higher, not 1K, not 2K, but 4K and even 5K screens. And this last month, the last dream of Bart has opened up, the digital conference room, and here you remember the concept Bart designed in 1986, that you should look at tilted screens. And here, the 42 participants can do video conferencing with other clinics worldwide, and they can discuss with the other disciplines within the hospital, and everybody looking at his own screen and to each other. It's not in a college, in a room setting. So, to end this talk, Bart, the start of your splendid career was quite disruptive. We didn't expect this all. It gave our department an image, tremendous boost in image analysis, totally unknown for us. We got 3D to assist clinicians, but also ourselves. PACS is normal in the daily web network for teaching and research as well. And last but not least, this year, the World University Rankings published that among the 10 best departments is Utrecht University, and you are really part of that success. Bart, thank you for everything.
Thank you very much for this beautiful overview of how things have changed since the very start of your career and how it's all due to you. Continuing with the early history of Bart de Haar Romeny is Professor Max Viergever. He's Professor of Medical Imaging and Director of the Image Sciences Institute, also at UMC Utrecht. As said, in 1989, Bart moved from the Department of Radiology to the group of Max, at that time known as the 3D Computer Vision Group.
Beste Bart, beste Hetty, dear ladies and gentlemen, it's an honor and a pleasure to give this presentation today on the occasion of Professor Bart de Haar Romeny's retirement. I've known Bart for more than 30 years, since the mid-80s, when I was still working in Delft, but was an active participant in the Utrecht Working Group on Medical Image Processing, which existed since the end of the 70s. And Bart joined this working group around 1985, together with Paul van Waas and Karel Zuiderveld, from which moment onwards we intensified our collaboration, and it was a pleasure to be in the Image Sciences Institute together as of '89, when you moved over to the Institute. As a physics engineer from Delft, you started a PhD project in Utrecht in 1979. The cover of your thesis has already been shown by Paul. The subject was organization and control of motor units in human upper arm muscles, the physics department of Utrecht. And to give you an idea about the experiments that Bart carried out, I have two figures from his thesis booklet. This is the first one, the experimental setup that he used, which looks much less organized than Bart is nowadays. And the second one is a nice picture of a muscle force measurement apparatus. And this already looks a little bit like a scanner, so may have been indicative of the next career move of Bart, but some of you may rather think of it as a washing machine when you see this. The fascination you had, Bart, for biophysics has remained ever since, but has been extended by two more research areas of interest: computer vision and solving real-world medical imaging problems, especially in radiology. And Paul has already given quite a bit of flavor of Bart's efforts to bring radiology to the 21st century. So I will concentrate more on computer vision, and Bart's love for this field was spurred by the pioneering work of Jan Koendrink, professor at the physics department in Utrecht, and of Steve Peiser, professor of computer science in North Carolina, who visited Utrecht in 1983-1984. And this article by Jan Koendrink was actually quite seminal for the field of computer vision. Koendrink was a renowned expert in human vision. He used his knowledge of this field to translate it to computer vision. Basic idea is that humans, when they look at the scene, see not only that scene as a whole, but also all sorts of details. So when I look into the hall, I see a hall full of people. So thank you very much for all joining us today. But I also can focus on individuals, or even to an individual's face or clothing or whatever detail you would like to see. And the nice thing is you can even do that simultaneously. So Bart picked up this idea and started to use this shining example from the human visual system to do image processing in this way. This is an MR image of what we had in the 80s, let's say, 87 or so, something like that. So that's about the quality we could produce at that time. And what Bart did is use the properties of the human visual system to build an approach which he coined scale space. And what you see is that you don't have only the image at the original resolution, but also all sorts of smoothed versions of that image. And that made it possible to look both at details and at the image simultaneously and to improve on image processing algorithms. The most frequently used kernel that we used was the Gaussian kernel, and the derivatives of the Gaussian formed a toolbox, and with this toolbox we could analyze all sorts of images. And we played around quite a bit with that, both with synthetic images to understand the properties and also with real-world images. And this is just a toy example of what we did there. The Dom Tower. And you see, for instance, by having the scale space and the derivatives of this Gaussian, that you can see edges of structures much nicer than in the original image. There are many more nice results, but you will see most of these in the talks later today, so I will not delve into that now. I already mentioned Professor Steve Peiser, University of North Carolina and Chapel Hill. He was in Utrecht twice, once from 83, 84 for a year, and once for half a year in 92. And he had lots of discussions with Bart about multi-scale image analysis, but also about quite a few other non-scientific things as well. He became a very good friend of Bart and Hetty's. Unfortunately, he cannot come to Eindhoven today, but he was so kind to send us a video message that I will show now.
This is Steve Peiser from the University of North Carolina. Bart Haar Romeny and I have been friends and colleagues for more than 3 decades. I was honored to be at his inaugurale oratie and to be getuige at the wedding of him and his lovely wife, Hetty. I watched with admiration, trying to provide a bit of help, as he set up the PACS unit in the radiology department at what was then het Academisch Ziekenhuis Utrecht, a unit which later turned into a leading medical image analysis research unit. Likewise, I admired his teaching of many doctoral students in that unit and was impressed when he finally was named professor at TU Eindhoven. There, he organized the productive research unit in medical imaging in the biomedical engineering department and energized the important connections between image science theoretical research and applied medical image analysis research for computer-aided diagnosis that we find there today. I admired his idea and execution of basing image analysis teaching on Mathematica. In Bart's Utrecht and Eindhoven posts, he influenced a great number of doctoral students and faculty colleagues, which have led to the very large number of publications of which he is co-author. And he has influenced my teaching for years, and still I have used his books on front-end vision and his edited volume on geometry-driven diffusion in my own course teaching. The aspects of Bart's career that I most greatly admire is the effect of his great teaching talent. I am wowed by his great teaching not only in Nederland, but also in Northeast China. I wish I could be in Eindhoven today to hear his afscheidscollege and to celebrate with him. Allerbeste voor de komende jaren, Bart.
Within a few years, I'm talking now about the early 90s, scale space was a hot research issue in the computer vision community. And here you see a number of scale space scientists gathered at that time. People like Guido Gehry, Olaf Küppler, Pietro Perona, Jitendra Malik, Luc van Gool, Ros Whittaker, and of course the Utrecht crew that was there. Picture taken at European Computer Vision Conference in Genova. And Bart, by that time, had also gathered a nice group of PhD students and postdocs working on multi-scale image analysis. And this group was usually referred to as Bart de Haar and the Romany's. Luc Florac, Alfons Salde, Wiro Niese, Robert Maas, Bram van Ginneken, and postdocs Mes Nielsen, Joachim Weikert, and Stilian Kalitsin. A very nice group of people, all very productive in science. And you will see quite a few of them later today. 50 years that Bart spent on multiscale image analysis in Utrecht were very fruitful. There were many scientific articles, of course, PhD thesis, and no less than 3 books, 2 of which I've mentioned already, by Steve Peiser also. Used the first book very much in his courses, but many people did that. It was really a landmark for this field. I think it came out in 1994. And then the middle book hasn't been mentioned yet, but it is a book on the conference that Bart organized in Utrecht in '97. And it was called, that's rather presumptuous at that time, the first international conference on scale space. We didn't know at all whether there would be a second conference. But you were right, of course, Bart, because it had many successors, and it's in fact still a continuing series now. But you were not really a person to easily delegate tasks to other people. You carried out all sorts of tasks yourself. And maybe that was because some assignments given by you did not always work out the way you wanted them to. I will give 2 examples. One is, refers to Karel Zuiderveld. You've seen this picture already in Paul van Waas's presentation. Karel was working in our group and had this marvelous piece of technology, a Silicon Graphics 02. And Bart had asked Karel to couple this, to connect this computer to the MR scanner so as to enable faster processing of images. And what happened was this. So Karel took the assignment of connecting the computer to the scanner a little bit too literally. And it took quite some effort and time and money because the MR scanner had to be quenched to separate the computer from the MR scanner again. This is the second example. An assignment to our secretary, Margot, 50 copies, please. Which Margot, and dan geniet. Which Margot understood as 50 copies, please, enjoy. And she felt outraged by such a request. And was happily relieved when one of our PhD students, who happens to be the chair of today, explained to her that Bart probably had meant the other very distinct meaning of the word geniet, which is stapled. So, but such accidents were rare. In fact, Bart scored many successes and even established many records in that period. And the remarkable one is that Bart had the largest fraction of cum laude PhD graduates. Of the 4 you had in Utrecht, 3 got a cum laude PhD, and the first one in Eindhoven also got a cum laude PhD. So of your first 5 PhD graduates, 4 got a cum laude, which is really remarkable. And all these 4 will give talks later today. Bart also holds the record of the shortest PhD project that was supervised in Utrecht. It concerns someone who enthusiastically started his first day, and at the end of the first day, after having left the hospital, phoned us to say that research was not really going to make him happy, and he announced that he would leave for France the next day to pick grapes. You still remember that, Bart? He mentioned in passing, by the way, that he did not expect to receive a salary for that one day he worked. This might suggest that Bart was not a good supervisor, but the contrary is true. The contrary is true. I know no one who is better able to stimulate students than Bart. He enjoys teaching and lecturing very much, and is also able to transfer his own enthusiasm to his students, his colleagues, and his audience if he talks for an audience. With multiscale image analysis, Bart had combined 2 of his fascinations, biophysics and computer vision, and the third one I mentioned was solving real-world medical imaging problems. This is an example of segmentation of MR brain images. He also worked in other fields like texture analysis of lung radiographs, and even delved into other medical disciplines like obstetrics in detecting ovarian follicles from ultrasound images. So in this way, Bart succeeded in combining his three main scientific fascinations by working on biophysically inspired computer vision for solving medical imaging problems, which nicely covers the 30+ years of research in Utrecht and Eindhoven, also covers the program that you will further hear today. Bart, thank you very much for the times we shared, and I wish you, Bart and Hetty, all the best in the time to come. Thank you.
Thank you very much, both of you, in fact, for recalling all these tales and all this work from a period long time ago. I think a period many of us here have not witnessed personally. And it was great to hear. It's now my pleasure to welcome a guest from abroad, our next speaker. It's Professor Alfred Broekstein. He holds the Ollendorff Chair in Science at Technion in Israel. And at least one of the times he and Bart worked together was not that long ago, when they were chairs of the Conference on Scale Space, there it is again, now combined with variational methods in computer vision in 2011.
Okay. Thank you very much. It's a great pleasure and a great honor to be invited here. I don't even remember when I first met Bart. It seems like forever. And I think it might have been at one of the Scale Space conferences, and the most memorable thing that happened is that we went to these Scale Space conferences, and then at some point my colleague Ron Kimmel at the Technion was my student and became a member of the community, told me, why don't we put a proposal to have the conference in Israel. And at some point we did this, and we had a discussion about this, and many people were afraid of coming to Israel for obvious reasons. You know, it's the Holy Land, but it's a very troubled area. And then, surprisingly, Bart came and said, oh, it's wonderful, it's peaceful, it's quiet, we can go there. And we had, we won the bid to organize the conference in Israel, and Bart was co-organizer, and we had a fantastic conference, which is very, very aptly, at a very apt location. You know, the conference we had was at the Dead Sea. The Dead Sea is the lowest point on Earth, and scale space and variational method is about finding minima, okay? So we went to the global minimum in order to have the scale space and variational methods conference, and this is in fact all about optimization and finding minima. So I was asked by Bart to tell you a little bit about scale space and variational methods and how they evolved. And actually, if you now look at the literature on image processing and computer vision, it is dominated by a few paradigms. The one paradigm is optimization. You are looking for the best. But often, the best is described by some criterion, and how do you design the criterion is is a very subjective thing. So therefore, you have to design criteria in a nice way. And then there is the other aspect of the problem is how to model your signal. You know, your signals are coming from some place. And Bart, being a physicist, he knows that there are certain processes, there are certain things that generate these images, and therefore they are not just random images. They have structure, and this structure can be modeled. So you have to put in a model for the signal. So you combine a model, you combine a model for the distortions that you have, and then you can talk about optimization. And it was at some point that there were two conferences running in parallel. One was scale space and the other one was variational methods. and the two conferences joined together, and today there is a very successful series of conferences that is called Scale, Space, and Variational Method, and Bart is one of the founding fathers of the field. I prepared a talk which was a little bit too technical for this audience, but I'm going to give you a tiny example of what I mean when I say that we are working on these parallel aspects of modeling and well, I'm going to start here. Here is a minimization problem. So we are very often given a noisy signal. Signal is an image, okay? The signal is this M of t, and N is a noise, is an unwanted disturbance that is added to it. Now, when I say that we want to recover M when we are given this R, which is a distorted signal, we want to minimize M. We want to find the minimization of a functional of this M, which combines two terms. The first term is how close is this R to the original, how close is M to the given R. R is given, and the second one is some information about the signal M. For example, you would like the M to be very smooth, and when you want M to be very smooth, you take its derivative and you integrate the changes of its derivative, and this gives rise to something that dominated in the past few years the variational method. It's called the Rudin-Osher-Fatemi framework. And here I just rewrote the Rudin-Osher-Fatemi framework in terms of M dot in order to put it in a form that I'll want to use a little bit later. Don't pay too much attention to the equations because they are not important. What is important is that you can then discretize the problem, and you have a discrete problem in which matrices are involved. And then what you have is you have a model for the signal which is of the following form. You have a signal that is a composition of known functions, of known phi i's, and they have coefficient functions which are also functions of the variable parameter t. T can be x and y in an image. Okay, so what you have now is you have a model, and you have an optimization criterion, and you want, as we all did at the global minimum at the dead sea, you want the optimal signal. Now, when you write these things, you write this functional which has two parts. One is how close is your model to the given data, and the second one is how do you measure the variations of the coefficients, and this is called an over-parametrization model. So today we are in the era of over-parametrization and sparsity. Okay, so the people went into this area of sparsity. So I want you to concentrate on a very, very simple example. Suppose that your image is, or your signal is just made of piecewise linear functions. So if your signal is made out of piecewise linear functions, then this is your model, and it's an artificial model, but it captures what it is all about. Now, if your signal is piecewise constant, it can be written as 1 multiplying some coefficient which will change, and t multiplying some coefficient which will change, but these coefficients will be piecewise constant. And this is putting a lot of constraints on the model that you have. And then the question is, how do you impose sparsity? Now, piecewise constant signals are sparse in the following way, that if you take their derivative is very, very sparse because it's mostly either 0 or a delta function in some right way of measuring it. And the coefficients have to change according to this sparsity model. And recently we combined all these things, and let us just present the result. So here is the problem. You have a signal which is piecewise linear, and you have the noisy version of it. So what you would like is from this noisy version of the signal, you'd like to recover the clean one, okay? So then you write the over-parameterized representation for the piecewise linear function, and you do the sparsity-based solution in which you want to recover the coefficients, but you want to recover the coefficients that are piecewise constant, and they have jumps that jump in synchrony. Now, this is an interesting problem, and it leads to another new type of optimization problem, and this gives better and nicer results than before for this particular problem. So look at this line fitting experiment. This is the real signal. The real signal is the blue one, and the red signal is the one that you are recovering. And here you can see that the coefficients are jumping and they are piecewise constant. And this is something that we enforced, okay? This is something that we enforced, and this is something that we can enforce using sparsity. So the buzzwords are variational methods, modeling of a signal in a sparse model, and doing the recovery based on these two principles. And this is much, much better. This yields much, much better results than other alternatives due to the fact that you are talking from an understanding of the signal model, okay? So the idea is that you have to essentially exploit the model of the signal. And this is a message that is extremely, extremely important and is sinking into the community. And we are making progress in this domain. So from 1D you can go to 2D, and here you can see an original signal which has this band, and there is a background which is changing, and this is an image. This is the noisy version of the signal. This is the standard PSNR recovery with the Rudin, Osher, Fatemi, which was the reigning method before. And when you do these new methods, you are getting much better results. PSNR is something that measures the quality of the recovery, and you have to have these numbers higher, as high as possible, and you can see that you can easily beat the reigning methods. And it is an interesting example because you can see that using the model you are getting quite good results, and you can do it for other images, and you can also use this for other signal processing tasks like segmentation and other problems like inpainting and so forth. But I'm not going to tell you about this. I'm going to just say the following thing. Retirement is a waypoint in our life. Okay, we are reaching a point where we have to retire, but in academia, retirement has absolutely no meaning. Bart, this is a nice event. We are celebrating you. We are celebrating 30 years of work and maybe more than 20-something years of meetings, but you are not retiring. I'm telling you there is going to be absolutely no change in your life. don't expect now that you can go fishing. You are going to continue your projects, and we are going to meet at conferences and at many, many events. We are organizing a beautiful summer school in Romania together, and we'll continue to do so very often, I hope. And you have your project in China, which will go on. And what is beautiful in academia is that our enthusiasm will never cease because it is fed by the enthusiasm of the young people around us. So congratulations on this waypoint. It's not a retirement, it's a celebration. Congratulations.
Thank you very much for your presentation, and especially for your presence here. It now pleases me to welcome Professor Luc Florac to the floor, because Luc is in fact Bart's very first PhD student. He graduated in 1993 with a distinction cum laude, which was a great start to your career, of course, but also to Bart's career as supervisor, because we just heard from Max that it was the first cum laude in a line of them. And well, it's no surprise then that you're now professor of mathematical image analysis here at Eindhoven University of Technology.
Yeah. Okay, thanks again. Bart, you told me explicitly not to talk about your research, so I will not do that. You asked me to talk about my research. Okay. And fortunately, previous speakers took the opportunity to talk about your research, your history, your interests. So I can continue. Promise to talk about my own work. If you want to have more details about Bart's work, I simply refer you to his website, where you can find all the details. As for me, I sort of became a literary pirate in the sense that I'm constantly cribbing ideas from the great scientists in the past. You see a couple of names here, a couple of faces. None of them are alive. So that's why I could shamelessly steal from their ideas. Oh, there he is. I was not going to talk about Bart today. I would like to mention, though, one scientist still alive that I think properly belongs into the same gallery as on the previous slide, and I think Bart shares my esteem for him. That's Jan Koendrink, here next to his wife, Andrea van Doorn. Jan Koendrink was together with Max Viergever, my promoter at the time, and Bart was my daily supervisor. And, well, at the time I did my PhD, this was sort of the motto. It starts with pixels. But Jan Koendrink had a sort of refractory mindset in this sense. So this is a famous quote from him. I've sanitized it a little bit, but I think it concisely conveys his ideas about image processing. So he thinks that, okay, everyone, the whole world at the time was thinking that, well, images consist of bags of pixels, and so image processing must be manipulating pixels. Not so Jan Koendrink. He thought pixels as something like a necessary evil due to real-world constraints. And I took that advice. So my thesis was more theoretically founded at the time. That was rather new. Always asking whether things that work in practice also work in theory. So, but if not pixels, then what else? Well, and that's the thing that Bart has been pursuing also, and Jan Koendrink, all the time, to take inspiration from the visual system, because the visual system has solved a lot of image processing problems for us. And so we can derive a lot of inspiration from that. And if you look into the visual system, you find very intriguing things. Like here we have the so-called cortical columns. It's an arrangement of visual cells that are in the brain that are looking at a specific point in the visual field. And as you can see, it's not a coincidental arrangement. According to this Japanese researcher, Shigeru Tanaka, we have a kind of Klein bottle symmetry in that arrangement. Well, I mean, if that's not a hint You know, you should try to figure out the theoretical mechanism behind that and exploit it. And most of the theoretical mechanisms behind it are not well understood. There are only very few exceptions. Maybe the case of microtremor in the eyes, that has been explained as a mechanism for super resolution. And once you understand those mechanisms, you can use them to your financial advantage and build reverse engineering applications and sell them for a good price. So here, this camera is built on that idea to use microtremor for obtaining super resolution. But most of the mechanisms we don't really understand. So that's for the inspiration part. And now for the motivation. It has, there has been a study commissioned by the European Brain Council to investigate the economic impact of brain disorders in Europe. And this was over 2010. The study took place in was published in 2012. And it shows these staggering figures, almost 800 billion euros annually spent on, well, economic costs that are incurred by brain disorders of one form or another, only in Europe. And maybe you've seen the news item this week on the Dutch television, that the observation that 3.8 million people in the Netherlands suffer from some form of brain disorder. That's in line with these figures, by the way. So it's basically nothing new, but it is really remarkable. And the main recommendation in the executive summary of this study was also to invest much more in brain research. So that is also what brings me to my current topic. And that's the fusion-weighted magnetic resonance imaging. This is an expensive hobby. We don't have these things anymore in Eindhoven. But as I mentioned, I'm looking at a more theoretical point of view, so that's not really an obstacle. And we're collaborating with partners worldwide on this. So let me explain a little bit about diffusion. I will not go into the details because I have only 15 minutes. But the idea is that with an MRI scanner, you can obtain signals for every point in the brain, basically sensitized for diffusion of mobile hydrogen, say water, in a particular direction. So you can do that for every direction, and there is a control parameter in the scanner for that. It's known as the Q-space parameter, which is proportional to a gradient magnetic field that is applied in the scanner on top of the static field to probe diffusion of water in a certain direction. And you can measure that. So basically you get a 5-dimensional image, one for 3 dimensions for position, 2 dimensions at least for the orientation in which you probe the system, and could be even 6-dimensional if you also allow the gradient magnitude to be varied. And you can see the more popular diffusion tensor imaging model, maybe most of you have heard of that, as a kind of dimensionality reduction of this thing. It produces, it brings us back to 3 dimensions basically, but in return for not a scalar signal, but a symmetric positive definite contravariant rank 2 tensor valued image. So that's a rather abstract thing that you cannot hope to understand by visual inspection. But we could try and understand this by visually inspired geometry. So if you understand how the visual system works in theory, then maybe we can apply that also here. And so that I followed Jan Koenring's advice to step away from pixels as the basic elements because they are much too rudimentary. They make some sense for problems like segmenting anatomical images. But in this case of tractography, which is the endeavor to reconstruct the axons in the brain, the white matter pathways, say, it makes more sense to look at other primitives. So here, the idea is to exploit this capability of the scanner to look at not only points in the brain, but also orientations probed by the scanner. And this brings us to a representation where not pixels, but rather line elements. So-called line elements are the basic building blocks. This idea is reminiscent of Einstein's idea to find certain curves in space corresponding to free fall of particles. They are known as geodesics. The idea is that these line elements, there are, say, you can think of them as infinitesimal vectors attached to each point, furnished with the notion of length. And if you shoot particles in the direction of such a vector and let it undergo free fall, it will follow a certain path, minimizing length. And that is called the geodesic. And that's actually completely analogous to the way Einstein geometrized the way the gravitational forces that are magically acting at a distance into the local geometry so that they manifest themselves as pseudo forces. So this is basically what we do, and let's see how that works in diffusion tensor imaging. What you basically can reconstruct from a MRI scanner is a diffusion tensor which you can map on this ellipsoidal gauge figure. You can think of that gauge figure as a sort of fuzzy confinement region for mobile water molecules. So here, water molecules are more likely to diffuse in the direction that is aligned with the underlying fibrous tissue. So that's the hypothesis that this microstructure of the brain imparts non-random barriers to water diffusion. So that's what you will observe in the anisotropy of this electron. And so the Einstein trick is to view this extrinsic process of diffusion in Euclidean space as an intrinsic process by hiding it in the geometry of some curved space. And here's how that works. So the idea is you interpret that ellipsoidal gauge figure as a unit sphere for measuring length. Well, locally, that's easy to do, but if you want to do this globally, you have to deform space. And that's how you end up with a curved Riemannian space. So we have a curved Riemannian space, and we can measure lengths that, in a sense, adapted to the diffusion tensor imaging measurements. So let's see how that can be used for tractography. So we have here the gauge figure. So we want to be able to measure lengths of curves. So we start with an infinitesimal vector. And we want to measure its length. Well, you can use the gauge figure for that. Just draw the vector and draw the tangent cone from the tip of the vector touching this ellipsoid. Draw the parallel plane through the tangency points and to the midpoint of this ellipsoid, and you have two planes with a certain separation. Now you can progress these planes in the direction of the vector. You get a stack of planes. This stack of planes is a pictorial representation of what is known in geometry as a covector. Covector and vector together determine a number, which is simply the number of times the vector pierces the covector. So that's 6 in this case. And this number 6 is, by definition, the squared length of the vector. So here we have a vector of length square root of 6, 2.4. And the idea now is, as you can see by the anisotropy, if I rotate this vector in a Euclidean sense into another direction, then the same vector acquires a different length, namely square root of 9, which is longer. So that means that if we want to follow curves that are aligned with the underlying fibrous tissue in which diffusion is facilitated, we should look for shortest curves. And that's so that's basically what we do. And then, of course, the problem is how do you relate the diffusion tensor to this gauge figure? So the oldest idea was simply to identify the inverse of the diffusion tensor with the so-called Riemann metric. That's basically this gauge figure. And there are some adaptations, like on the right-hand side, an adaptation by Andrea Fuster, who looked at the axiomatics of water diffusion on the Riemannian space. You get something proportional to it, but it's slightly different. And it also results in slightly different tractography results. This is from a MICI challenge, where we see that on the right-hand side, well, results are qualitatively similar. On the right-hand side, though, we do not observe any of the paths crossing the ventricles. And we know this would be nonsense, but this happens with the naive choice of the metric on the left-hand side. Okay, so it's just an illustration. So what I was arguing is that we should use rather line elements as primitives for tractography. But it's a fact that Riemannian space is geodesically complete, which means that any 2 points in the brain are connected with a geodesic. So there are geodesics all over the place. So you could say, in some sense, we have 100% false positives if you would interpret geodesics as fibers. Of course, that's not the point. They are primitives, just like pixels are primitives for an image. You don't interpret pixels as part of a segment because you still have to do the segmentation problem. Here, we still have to do the pruning and remove those geodesics that do not likely correspond to fibers to end up with the more plausible fibers. So this geodesic completeness I consider actually a good thing for an a priori representation for tractography. There's also a drawback, because you see these, by definition, these gauge figures are ellipsoidal. They are determined by 6 degrees of freedom, the coefficients of, say, the DTI matrix. And that means that there is a poor angular resolution in the sense that nowadays we can measure these diffusivity profiles in the scanner locally with many more degrees of freedom to more angular sophistication. But we can't match that to the geometry because we only have these 6 degrees of freedom in our gauge figure. So that's a drawback of the method, and that also explains that it doesn't work very well in the case where we have complicated underlying anatomy, such as crossings and things like that. And they happen all over the place in the brain. So this is a drawback. And so that's what I wanted to repair. Well, nowadays, I mentioned DTI is, well, in the old paradigm, DTI could be coupled in a one-to-one way to Riemannian geometry, because there was this one-to-one connection between the gauge figure in Riemannian geometry for measuring lengths and the degrees of freedom of the DTI tensor. Now, DTI, so this is a bit awkward in the sense that DTI, that this model builds upon the limitations of DTI, because DTI is now is a limited model. We have more sophisticated models here nowadays, known as high angular resolution diffusion imaging models. And we lose this one-to-one connection with the geometry. Unless, of course, we also generalize the geometry. And the most natural generalization of Riemannian geometry, already anticipated by Riemann himself, by the way, is tensor geometry. And then you can reestablish this one-to-one connection again to geometrize away your diffusion information into the geometry of your space, which is now then called the Finslow manifold. And there's only one thing I would like to explain about it, because the mathematics is too mind-boggling to explain in 15 minutes. And I'm not sure how I am in time now. A few minutes, yeah. So I just want to explain the essence. We extended space from 3-dimensional to 5-dimensional because we have this orientation degree of freedom for probing diffusivity. So we have a 5-dimensional space that is known in geometry as a tangent bundle or cotangent bundle. But in a way, you're interested in curves in real space, in 3 space. So you need some kind of projection principle to look for the physical curves of interest. This is dimensionality reduction. We heard sparsity. So we are extending our space, but we want to see the physical processes in 3 dimensions. And there's this notion of horizontal-vertical splitting that does it, and you could illustrate it with this figure skating on the left. So the vertical type of motion, when you move in this 5-dimensional space, would correspond to a spinning motion that is not in sync with your translation. So for instance, spinning on the spot, you change your orientation, but you're not moving. You're not moving around in space. That's a pure vertical motion. In technical terms, it has it's spanned by basis vectors, which are just given by the orientation basis vectors. And the other type of motion is so-called horizontal motion. And horizontal motion is a careful balance between translation and spinning. It's precisely the balance that you have when you walk in a normal fashion. So when I translate like this, and then I make a turn, I also change my gaze accordingly. So that I'm always looking forward. So that's a very particular motion in this 5-dimensional space, and that's called the horizontal motion. So that's illustrated by this skater that's making a smooth curve, but keeping the gaze aligned with her direction of motion. And of course, you can combine the two. So skaters typically explore the whole tangent bundle. They do these spinnings and translations sort of independently. But we are interested in the horizontal type of motions. And there you see that what you need, I don't know whether I have a pointer here. The essential thing you need is some kind of coupling between it. This represents a translation, and this represents a spinning, and this is a coupling between translation and spinning. That's precisely this synchrony between translation and spinning that you need for a horizontal motion. And it's in these coefficients, they are known as the nonlinear connection coefficients, that the geometry really resides. So that's what you need to understand. And this geometry manifests itself in the equations of motions for a geodesic, and therefore equations of motions that give you candidates for your neural fiber bundles. And they manifest themselves as pseudo-forces. So the equations look like Newton's law, which says free fall means zero acceleration. But in this case, we have pseudo-forces induced by the geometry, and they're exactly those nonlinear connection coefficients. These pseudo-forces, they pull yourself towards the Finslerian manifold. So that makes that your actual curves are not straight lines, but they follow the geometry. And as we know, this geometry is induced by what we measure in the scanner. So as to obtain shortest paths that are most likely, or some of which most likely correspond, hopefully, to neural fibers. So the conjecture is that a neural fiber, or a bundle of fibers at the resolution of measurements, is a member of a geodesic concurrence, of a family of geodesics. There's some caveats. I already mentioned that a typical geodesic does not correspond to a neural fiber. This is the 100% false positive case if you play the devil's advocate of the devil. You say geodesic tractography doesn't work because the geodesics do not correspond to fibers. But the problem really is to find those geodesics that do correspond. And I don't think this is really a solved problem. We are getting closer, but there's a lot to be done there. But think of it as follows. I'm now collaborating with a neurosurgeon. And if a neurosurgeon says, I know for sure this point is connected to this point, then I have to give him a connection. Okay. I'm done almost. I have to give him a connection. If you use the old-fashioned streamline method, odds are that you will not find that connection. So this geodesic completeness is in fact a good thing, but you have to search deeper for criteria to decide whether certain geodesics, maybe in a probabilistic sense, correspond to neural fibers. So that's one caveat. Don't confuse geodesics with neural fibers. A neural fiber is not necessarily a minimal geodesic, so it's not necessarily, doesn't necessarily give you the shortest path between 2 points. Only locally, these paths are shortest paths, but globally there can be shorter paths, which are also geodesics. So you can have multiple geodesics connecting distant points. And that's also often overlooked, depends on how you implement it. So you can implement it in a way that enforces a single solution, and then you may miss actually the geodesic that you want. And so that's the last point, the ambiguity of connections between distant points. So this is all reminiscent of Einstein's way of geometrizing gravitational forces. The mathematics is quite similar, but it's more general in this Finslerian extension. And so we can get more complicated situations. So I started, actually there's some books that if you're interested, I would recommend. These are the 2 books that I consulted. Nowadays, there are books being published on an almost weekly basis. So to wrap up, we started thinking the world is flat. Then we saw the need for a Riemannian manifold with the advent of diffusion tensor imaging. And that turned out not to be sufficient, so we had to generalize even further and obtain a Finslerian geometry, which you can think of as an infinite family of worlds, one for each orientation. So Bart, this ends up my talk. You still look the same as before. You haven't aged, so that's a good thing. And, well, as Alfred already mentioned, this is not the end. This is just a continuation. Actually, I think it's an excellent opportunity for you to try and put all the ideas you've gathered over the years into a new book on the visual system that starts with chapter 1. But of course, in your new life, it's up to you to fill in the details. And that concludes my talk.